Thank you. It's a pleasure to be invited to speak at this 30th anniversary session for SD&A. When Andrew asked me, I thought, well, actually, why do I come to this conference? So I'm one of the frequent flyers, maybe not as frequent as our first speaker, but and I think it's always had a really good mix of industry and academics, and talks about a wide range of topics from new devices to a range of applications. And finally, it's always been welcoming to people like myself who are interested in vision science and visual human factors. So I went through the 30 years, so we can see it plotted along the x-axis here, the different years. And the light gray is the number of papers that year, and you can see that it's ebbed and flowed. The dark gray is the ones that I've sort of arbitrarily classified as a vision science paper using, very idiosyncratic criteria. But you can see it's followed very similar pattern to the conference as a whole. And also, it's one of the few places where we can actually present stereoscopic 3D content. So the glasses are going around now. Another attraction is this is the York University campus in January. So coming to San Francisco is also very nice. The very first paper and the very first proceedings was by Christopher Witkins, and it talked about guidelines developed from human visual capabilities. So right from the start, visual human factors and vision science have been welcomed here. That very first conference was also the, I believe, if not the first time, one of the first times that Christopher Tyler presented his autostereogram, and there's a festschrift in the Human Vision Electronic Imaging Conference to him later in the conference. There have been several keynotes that are vision science related. Ian Howard, my PhD supervisor, gave one. That was the first time I actually attended SD&A. Jenny Reed and Andrew Glenister recently, Andrew last year. And I'm not sure if John would consider himself a vision scientist or not, but he certainly has lots of interesting things to say about vision science. Some of the topics that have been common, vergence accommodation conflicts, alignment and calibration, and disparity control, among others. My talk today is particularly about geometry and distortion, and how we can predict distortions from geometry, but that may not necessarily be what we see. This has a long history as well. So this image on the side is from Andrew Wood's very nice 93 paper, where he's looking at visualizations of various distortions that you predict purely from geometry when doing various things to your stereo rig. So here's a towed-in stereo rig, and you get this curvature. This is parallel, so everything's flat, but it gets compressed with depth, and this is off-axis viewing, and so on. There's been other talks about orthostereo and things like that, and augmented reality. I included Neil Dodgson's 2004 paper. It's not really about geometry, but it was about the variation of separation between the eyes, which is a very important factor. And there was plenty more after this. There was also a lot of interest early on in eye strain and fatigue. I think this is my co-author's first paper in 2002. And there's been a lot of work to deal with these sort of issues by changing geometry. So for instance, this is Siegel and Nagata's work, where they took an input disparity map like this, where variations in grayscale represent variations in disparity, and they scale it down so that it's very flat, but find that you can still get, in many situations, an effective stereoscopic display. So there's been lots of interest in geometry, the predicted distortions you get from geometry, and then systems to deal with that. Okay. Whenever you deal with stereoscopic geometry, you need to deal with some shooting parameters, and I'm not going to go into them in great length, but two at least are very specific to the stereo camera rig. One is the camera convergence, or really the positioning of the image with respect to the screen, and the second is the interaxial, or the camera baseline, which is a critical parameter. It's important to remember, though, that things like focal length, magnification, all the regular photographic parameters also matter, as do the display parameters and the viewer parameters, the separation between the eyes, where the viewer is seated, and so on. To demonstrate this, I think the next slide just shows the effect of IA. So basically, as you increase the separation between the cameras, you increase the parallax in the images. And to first approximation, you're going to take stereoscopic space and stretch it along the z-axis. So for a small IA, you should expect to have fairly small depth in the scene relative to the screen, and for a large IA, you'll stretch it. So this gives us a parameter, sort of stretch space in a nonlinear fashion, but still ability to stretch space. So here's the first stereo demo. So we'll need to switch to the stereo, and you can put your glasses on. And this is just going to show, this isn't stereo yet, just going to show a number of spheres rendered with increasing interaxial from the bottom right up to the, is it up? Yeah. So it may get hard to view as you get up towards the upper left, but you should start, it should look fairly flat, and at some point it should look round, and then it should stretch, and then at some point you might have trouble actually seeing the depth at all. Okay? And this is just simply different renderings of the same sphere with different camera baselines. Okay? You're going to take a very similar image and present it. So this is the exact same spheres, the exact same disparities. What happened is the lighting is now from below, so this is an unnatural lighting, and you might find that the percept shifts a little bit. For me, I find I lose the upper limit of the disparity a little bit earlier. Okay, I think we go back to the regular presentation now. Okay. In the extreme, you get things like, I think the lens is sort of half over the image. In the extreme, you get things like miniaturization and gigantism. So if, for instance, you have a very large stereo baseline and, for instance, a high angle for the camera, saturated colors and things like that, you can get the sense that things are miniaturized. In this case, it's not stereo, it's done by tilt-shift focus, but you can get these distortions of space where you reinterpret things instead of as being large and far away as being near and small. Okay, it's sort of an extreme version of distortion from baseline. So it's important to remember, though, that when we view a stereo image or stereo media, we don't just have the disparity, we have all of the monocular cues, the pictorial cues to depth. So things like shadow in that example with the spheres I gave you, linear perspective, motion, and so on. And VR, 3D films, games, any 3D media adds stereopsis based on binocular disparity, but it's not like these other cues don't still play a role. And this is one of the reasons why we can't simply assume that binocular geometry is going to be the same as perception. And, excuse me, and so I'm going to at a couple examples of where this is the case. They're fairly simple examples, but I hope they'll demonstrate to you that this is true. Most of us know it, but this is a good reminder, I hope. So the next stereo demos, please. Yeah.
Seems to be okay.
Okay. Right. So you may so this is a scene of a natural scene, and you might notice that it might take you a little while, but you might notice that some things are funny. So if you pay attention, you'll see that some of these leaves that are on the ground are poking through the trees and so on. It's reverse stereo, yes. So this is a pseudoscopic image, which is been known since the early days of stereography to give two very interesting things. It gives you an impression of depth, often a very strong impression of depth, and it often takes a long time for people to figure out it's been reversed. Okay? Here it is in normal view. Okay? These are fairly magnified images, so you get a little bit of cardboard cutout in them. Okay? And here's another view from that same scene. So this is also reversed. And you'll notice that these trees, which are objectively far away, are much nearer than these trees. You might see branches poking in and out, and so on. So we did a study, okay, and let's see. Okay, so we did a study using a pseudoscope. We can bring the regular presentation back now, please. We did a study using a pseudoscope, which can present different left and right images to the two eyes, and we looked at the occurrence of these various phenomena. So geometry would tell you that everything would just reverse. Whatever is far would be near, and so on. Okay, but it's been known since the, sorry, I think I used the wrong remote. That you get a variety of appearances. So in the second image that I showed, many people found that the near trees, far trees appeared near, so you get this reversal of depth. Boater ownership seemed to change. The occlusion was due to the near tree instead of the far tree, and you get inversions of depth. The far branches in the shade appeared to be in front, and you get a variety of different phenomena. So we classified these based on observer responses into a number of categories. So almost everyone sees depth reversal. So they see the trees coming out in front of far trees coming out in front of near trees, and so on. Very few people see shape reversals. They see things that are convex appearing to be concave, and so on. But there are lots of distortions of size and flatness, border reversals. And a surprising number of people with good stereopsis don't see anything at all. They just see an image that looks fine. They don't report any pseudoscopic appearances. So you can see there's a wide variety of these pseudoscopic experiences, and this is for a case where geometry is essentially reversed, right? This is an extreme distortion of geometry. We flip the two eyes. As I said, it often takes a long time for people to experience the illusion, or experience the fact that it's been reversed. So these shows the effect latency against stereo acuity and against visual acuity here. You can see there's almost no effect of stereo acuity and a weak effect of visual acuity. So observers, even observers with very good stereopsis, or at least normal stereopsis, can take many seconds to detect this reversal. And this is true if you do a demonstration like this. It's often quite a bit of time before somebody figures out the images have been reversed. And once again, there's a wide variety of phenomena within the images and across observers. So it's not simply a reversal of geometry, it is a reinterpretation of the scene. The second example is a little bit simpler. So you might argue that's a complicated scene, all kinds of complicated things are going on. In this case, we're going to look at an image that's simply moved in depth back and forth. It should appear to be far away, come near, be far away. This is an anaglyph version of something like that. The interesting thing was found in the mid-'80s that a stimulus like this doesn't typically give any appearance of motion and depth to an observer. Okay, and I think it's best probably to bring the stereo displays up, and we can see if we can demonstrate that. So we're going to show 3 different versions of this. Okay, and we'll need the lights down for this to have a chance of working. So you might not see a whole lot happening at all here. In reality, this is going back and forth in depth. If you take your glasses off, you can see the change in disparity is actually quite significant. It's going back and forth in depth. And if we did this in a completely dark room, most people wouldn't see this moving at all. Okay? We can make it a little bit easier to see the motion in depth if we add a looming cue. Now most people should see it moving considerably in depth. Okay, so that first one had a conflict with the looming cue, the size cue. And finally, this last one, I don't know, if this was a very dark room, what almost everyone would see is the background being pretty much stationary and the dot moving in depth. If not, I hope you're at least seeing the dot moving in depth. And objectively, if you look, there's actually no movement in the dot at all the movement's in the background. Okay. Great. Can we bring the regular presentation back? So here's some data. So in controlled environment, if you just have the random dot texture moving with disparity, people on average report absolutely no motion in depth. If the random dot texture is associated with, it has no disparity, it's monocular, but it has a lumen Q, it has the size Q, then people all see it moving in depth. And if they have a disparity as well, they'll see it moving a little bit more. Interestingly, if you put the direction of the size Q completely opposite to the disparity Q, people will see it moving in the direction of the size Q. Okay. And we, just for interest, we did this with a self-similar pattern like this that doesn't change size as it goes, and people see the disparity much more there. So basically another example of where geometry doesn't predict perception. And then the final one, we're going to vary interaxial in full Q stimuli. So we have a number of experiments here. We varied screen size, convergence, motion, all kinds of things. But I'm only going to show you the effects for interaxial here. So basically we had subjects view a test scene to get a reference, and then view stimuli. Can we bring the last images up, please? Oh, sorry. This one's not as critical for the darkness, but. So this is a really simple movie. There's somebody reading in the background, and on the right-hand side, you've got an interaxial camera separation of 95 millimeters. On the left, you see 25 millimeters. Hopefully, you'll see a difference in depth there. And we basically just had subjects view these not side by side like this, but on their own, and make judgments of the depth between these arbitrary objects in the scene, these poles. Okay. We can go back to the presentation. Okay, so we had people make these judgments, very simple, between the poles in depth or lateral judgments, and did this under various conditions of interaxial. Okay, so just one graph I'm going to show. So this shows the interaxial along the x-axis and the depth along the y-axis. Geometric predictions, you get very strong increase in depth predicted from the stereopsis alone. The dotted lines show that. The solid lines show the actual data. And you can see that you do get an increase in depth with disparity, with the interaxial, but it's much less than you'd expect from geometry. And there's no significant effect for lateral distances. I'm just going to go a little quick because we lost a little bit of time switching to the 2D displays. One of the big things here is you've got this scene that's always the same. Right? And it gives you a sense of scale, gives you monocular cues. What happens if you use very simple cues, such as straight lines like this? Well, in this case, of course, you get much more depth, as you expect. It doesn't matter too much on the task. We get similar responses if we ask people to walk to the location or to reach, and so on. So then to summarize in this section, we had a clear effect of IA, but not as large of effect as expected. Similarly, we had small effects of display size, camera convergence, and so on. The take-home is really that the 2D cues play a significant role here, and you can't just simply take the stereoscopic geometry and predict the depth that you're going to see. So some of these distortions, some of this is good news, right? Some distortions are well tolerated. You can have variation in IA without necessarily causing problems in perception. However, you still need to respect the geometry. There might be subliminal effects. You might get motion sickness, eye strain, and so on. And in cases such as augmented reality, where you have a reference to the real world, then things can be much different because now you're judging disparities relative to the real world. And just want to finish by thanking my collaborators, and there's a number of partners that participated in this as well. I'd like to thank them as well. Thank you for your attention.
Thanks so much.